All right, let's dive right in. We're about to explore a world where the rules of reality, the ones we see every day, they just break down. Welcome to quantum physics, the absolutely bizarre science of the super, super small. So, where do we even begin with this stuff? Well, let's start with a question that honestly kicked this whole thing off. It's a puzzle that had scientists scratching their heads for centuries. And it's a simple one. What is light? Now, for a really long time, everyone thought the answer was pretty obvious. You see, if you take a beam of light and pass it through a really narrow slit, something funny happens. It doesn't just make a single bright spot on the other side. No, it spreads out, it interferes with itself, and it creates this pattern of bright and dark bands. That is classic wave behavior. I mean, it's exactly what you'd see with ripples in a pond. So, easy peasy, right? Case closed. Light is a wave.
Yeah, not so fast. Just when everyone was ready to pack up and go home, a new experiment popped up. And this one showed light doing something, well, something completely different. Something that, for a wave, should be totally impossible. This thing is called the photoelectro effect. And get this, you shine a light on a piece of metal and it can literally blast electrons right off the surface. Now think about that. That's not some gentle wave lapping at the shore. That sounds more like a stream of tiny, powerful bullets.
So what's the deal? Is it a wave or is it a particle? The answer that quantum physics gives us is, well, it's kind of astonishing. It's both. So let's meet the little guy responsible for all this confusion, the photon.
Okay, so instead of picturing light as this continuous, smooth wave, quantum physics says, nope, think again. It tells us to imagine light as a stream of these little individual packets of energy. And these discrete little bundles, we call them photons.
And here's where the photon's personality really gets weird. Look at this. It has zero mass. Zero. But it can still hit an electron within a force to knock it away, just like a tiny billiard ball. It zips through space like a wave, but the moment it interacts with something, bam, it acts like a particle. So here's the part that'll really bake your noodle. Light isn't deciding, okay, today I'll be a wave, tomorrow I'll be a particle. It's somehow both all the time. The nature it reveals to us, that completely depends on the kind of experiment we set up to observe it. It's like it knows we're watching. All right, let's really dig into that key experiment, the one that blew classical physics right out of the water and proved the photon was a real thing, the photoelectric effect. The setup itself is pretty straightforward. You've got two metal plates inside a vacuum tube, you shine light on one of them, and if the light has enough oomph, it kicks electrons off that plate. Those electrons then fly over to the other plate, and boom, you get an electric current you can measure. Sounds simple, right? Well, the results were anything but simple. This is where it gets super weird. See, if light was just a wave, then a brighter light, a more intense wave, should knock out electrons with more energy. Makes sense, right? But that's not what they saw. The energy of the electrons depended entirely on the light's frequency, basically its color, not how bright it was. And what's more, if the color wasn't energetic enough, you could shine the brightest light in the universe on it, and absolutely nothing would happen. Not a single electron would budge. And this graph just nails the quantum explanation. See that perfectly straight line? That tells you it's a simple one-to-one interaction. One single photon comes in and smacks one single electron, transferring all of its energy in that one hit. Turning up the brightness doesn't make each photon more powerful, it just means you're sending more photons. It's a perfect, clean, direct relationship that the wave theory just couldn't explain. So this whole photon idea was a huge deal. It didn't just solve the photoelectric puzzle. It also unlocked the secret behind something else, something beautiful. Why every single element in the universe has its own unique fingerprint made of light. Okay, so think about this. If you take light from something like a hot light bulb filament and shine it through a prism, you get what you'd expect, a full, continuous rainbow, every color blending into the next. But if you take a gas, heat it up until it glows, and then pass that light through a prism, you see something totally different. You get just a few sharp, specific lines of color on a dark background. It's like a barcode. And this wasn't just a cool light show, it was a massive clue. The fact that these atoms were only spitting out very specific colors or frequencies of light meant that something inside the atom itself had to be happening in specific, discrete steps. Energy wasn't a smooth ramp, it was a set of stairs. It was quantized.
This idea just completely shattered the old picture of an atom, the one that looked like a tiny solar system. Turns out electrons aren't just zipping around in any old orbit they want. Nope. They're stuck on specific energy levels, kind of like rungs on a ladder. They can be on this rung or that rung, but never in between. And when an electron drops from a higher rung to a lower one, it has to get rid of that extra energy. How? By spitting out a photon with that exact amount of energy, which corresponds to one specific color of light. And here's the coolest part. Every single element, hydrogen, helium, iron, has its own unique ladder, its own unique set of energy rungs. That means each one produces its own unique spectral barcode. And that is how astronomers can look at a star that's millions of light years away and tell you exactly what it's made of. They're just reading these atomic fingerprints sent to us across the vastness of space. It's incredible. Okay, so let's recap. We figured out that light, something we all thought was a wave, can act like a particle. But here's a fun thing about physics. The universe often loves symmetry. And that realization led one physicist to ask a question that was, well, completely wild. The year is 1924. A young physicist, Louis de Broglie, basically flips the entire idea on its head. He thought, okay, if waves like light can behave like particles, what if particles, things with mass like an electron, could behave like waves? And he didn't just suggest it, he wrote down an equation for it. Now, don't worry about the math. The idea is simple. It says that everything that moves has a wavelength associated with it. The more momentum something has, so the heavier it is or the faster it's going, the shorter its wavelength gets. For something like a baseball, that wavelength is so ridiculously tiny we could never hope to measure it. But for a tiny little electron, well, that's a different story. Its wavelength is actually significant. Now, this was a radical idea. And you know the saying in science, extraordinary claims require extraordinary proof. It's one thing to come up with a really elegant equation on paper. It's a whole other challenge to prove that it actually describes reality. And then, just a few years later, the proof came crashing in. Scientists fired a beam of electrons, which are definitely particles, right, through a thin crystal. And what did they see on the other side? This, a diffraction pattern. Those rings are a telltale sign of waves interfering with each other. It's a pattern that particles just shouldn't be able to make, but they did. De Broglie was right. Particles are waves. And that, right there, brings us to the absolute core of quantum mechanics. It's called wave-particle duality, and it means that everything, a photon of light, an electron, you, me, the planet, is both a wave and a particle at the same time. The version of reality we get to see, it all comes down to how we choose to look. And listen, this isn't just some weird trivia for physicists to argue about. This idea fundamentally messes with our very definition of what an object is. If everything is also a wave of probability, really, then where does the solid boundary of you end and the rest of the universe begin? It's a mind-bending question, and it just goes to show how much more there is to discover about the very fabric of our reality.